Thank you for staying so we can start. Very happy to see such a good crowd again. This is the second event in a series, and many of you were here, I'm sure, for the first one on global warming. Dr. Hansen really shook up a lot of us. Today we are fortunate to have another very distinguished speaker. He will be talking about what is, or can be viewed as really the other side of the same coin. Global warming, of course, as I think by now all of you are aware of, is due to the increase in the, primarily due to the increase in the carbon dioxide concentration in the atmosphere, and much of this we now recognize, and everybody recognizes, even Washington recognizes, is man-made. Now, of course, it comes from somewhere, and it comes from primarily burning fossil fuels, and the one that I want to concentrate for the next minute or so is oil. And today we are going to talk about what this depletion of oil and eventually, effectively, exhaustion of oil will bring during the rest of the century. It's a real, there are of course different opinions, but I think there is really universal agreement. We are in for a big sea change. It's going to be a different kind of world. And what kind of world will it be? What can we do about it? That's the subject of the evening today. And this brings me to the person of today's speaker, this evening's speaker, Dr. Steve Coonan. He is not a stranger to this campus. Quite a few of you are aware that we have had on this campus now for something on the order of a quarter of a century, the Institute for Theoretical Physics, renamed later Kavli Institute for Theoretical Physics. And I remember Steve Coonan here. I don't remember the exact year, but it must have been around 1980 or so. He was one of the early visitors to the Institute, and since he was just down the road at Caltech, and I think he liked it here, he came back quite a few times. Now, he had a very distinguished and even more unusual career. I'm not going to spend a lot of time. I was told to be brief. I'll just say that he spent many years at Caltech as a theorist and as a very broad theorist. That's one of his distinguishing characteristics. Many years after being a working theorist, he spent as provost and vice president of Caltech. And then in 2004, he changed careers quite radically, and I hope he will tell us about it. I think it's a very interesting story. He has now, for the last 2 or so years, been the chief scientist of British Petroleum. This is good news for all of us. British Petroleum was quite outstanding among the major global oil companies for quite a while. They recognized unashamedly that oil is not going to be lasting forever. Now you'd think that's pretty obvious, but it was denied, and is still to some extent being denied in certain quarters, particularly in the United States. British Petroleum, I don't know when they first began to say, well, the name really means beyond petroleum, but they were among the first to draw attention to the fact that oil will be running out. And now they have such a dynamic individual as Steve Coonan as their chief scientist, and that's good news. There's been a radical change, even among the oil companies. Now, the thing that struck me is just one little sort of indicator, a canary, so to speak, in the mine. There was one of the biggest oil companies, and I don't want to mention it here, about 4 or 5 years ago, I happened to see in the Scientific American, they took out a 2-page ad, left side and right side, and they said, oh, all kinds of people, and I think they must have had British Petroleum in mind as one of those people, are talking about oil is running out. I, the CEO of Company X, tell you, don't worry. There'll be oil, I guarantee it, for the next 25 years, nothing to worry about. Well, I happen to have seen the latest forecast from the Department of Energy, US Department of Energy. Now, they don't know when oil is going to peak, and so they had various scenarios, but roughly speaking, their idea was it's going to peak not in 25 years, but in 35 years. And Company X didn't say anything about 35 years. But many of us were waiting for the rest of the United States establishment and the rest of the big oil companies to fall in line. And that is happening. That same company took out another ad in the Scientific American about two or so years later, and that ad on one page had only one sentence, and that sentence said, for every barrel of oil that is used, only half a barrel of new oil is being discovered, period. Think about it. A real sea change. I'm happy to see it, and I'm happy to see people like Steve Coonan in a position of leadership for this sea change. I think you know how this evening is being planned. We're going to have Steve talk to us in just a moment. After that, we have a distinguished panel, and you've seen on the screen who they are, and I don't know what they will do, but we'll all find out. And finally, after that, you're going to have a chance to ask questions and to tell us what you think about this. So let's all welcome Steve. You know that. Okay. Fine.
So, good evening. It is a pleasure for me to be back here, a campus where I spent some of the most exciting and productive times of my research career at the ITP when it was still over in Broider Hall, just across the way. I suspect that just about everyone in this audience has seen Al Gore's movie. And, okay, good. You know, I found it rather disappointing or unsatisfying because while he does a very powerful job of painting a picture of the dangers associated with anthropogenic greenhouse gas emissions, he doesn't tell you what we should do about it. In fact, there's a little bit at the end. There's a voiceover over the credits where there's a list of things that is being read off. And so that's the subject that I'd like to deal with this evening. What is it that we can do about greenhouse gas emissions, and what should we do? In order to address that question, as Walter mentioned, you really need to think about energy, because energy is by far the largest anthropogenic source of greenhouse gas emissions through the use of fossil fuels. And remarkably to me, as I have come to learn about and talk to many people about energy, I find that there are tremendous misconceptions or even just plain afactuality in the discussion. And so what I want to do this evening is to take you through a largely factual description of the world's energy system. Where do we get our energy? How do we use it? What are the forces driving the world's energy system? And what are the technologies that we can deploy in order to respond to some of those forces? Greenhouse gas emissions among them, but there are others as well that have to factor into the equation. Okay? So we'll talk first about the forces driving energy, and then we'll talk about technologies. There are really four factors that are going to determine the world's energy future. One is the strong growth in demand expected over the next several decades. Another is the challenges in supplying the energy that is going to be required. There are issues associated with security of supply that we'll get to, and then there are issues of environmental impacts, climate change among them. All four of these, as they are balanced, will determine the technologies that we'll develop and deploy, and of course the policies that will be important in abetting that process. So let's start with demand growth. And the headlines here are, first of all, strong growth in demand over the next 30 years, driven largely by growing GDP in the developing countries, but also due to some extent to population growth. A second factor, which I won't discuss in much detail, is the growing urbanization of the world. Right now, about half of the world's people live in large cities of more than 1 million or so, and about 30 years from now, roughly 70% of us will live in large cities. And then, as always in talking about demand, there is the discussion of demand management or conservation and efficiency, and I want to say a few words about each of these. This chart, for me, summarizes so much about what has gone on and what will go on with the world's energy over the next many years. What's plotted is the energy use per capita each year in gigajoules. If you're not a technical person and don't know what gigajoules are, don't worry. You will see lots of different units in this next half hour or so. Barrels of oil, BTUs, quads, et cetera, et cetera. Just think increasing energy use per capita going up. Going across is a unit we can understand, that's dollars, in constant dollars in the year 2000, measured in purchasing power parity. And what are shown are evolutionary tracks of various countries over a 24 or 25-year period up until recently. And when you look at this chart, so many things jump out at you. The first, of course, is how out of whack the U.S. is with everybody else, way up on top. Okay? However, The U.S. energy use per capita is not growing all that rapidly. It's about 1% a year. Of course, the U.S. GDP is also pretty high compared to just about everybody else. The second feature that catches one's eye is a cluster of other countries in the developed world, the EU and Japan, in which energy use per capita is about half of that of the U.S., and also growing, although also relatively slowly, although look at France, that's going up somewhat. There are also some other interesting features on this chart. There are some fast movers. Look at the way Ireland took off over the last 25 years. There are also some countries that exhibit peculiar trajectories, retrograde motion in Russia. Clearly due, the Russian data, by the way, are only from 1992 onward, and that's due, of course, to all the economic turmoil that was associated with the breakup of the Soviet Union. And then most interestingly, there is a broad main sequence, if you like, of countries that are developing and are following a more or less universal trajectory of increasing energy as GDP increases. And what is sobering is that there are about 1 billion people in the US, EU, and Japan. There are about another 2.5 billion people in China, India, Brazil, and then there are about another 2 billion people who are not even on this chart. All right. And so as these countries develop, and as the US and the EU maintain their societies, we're going to see strongly increasing energy use in the world. The other factor that plays into this is, of course, the population. Oh, we're going the wrong way. The population growth. This is the world's population since 1750, and you can see it rises up quite strongly. By 2050, we will go from our present 6.3 billion to just about 9 billion, and will be pretty constant after that. Most of that growth will be in Asia and Africa, with, in fact, Europe and North America being relatively constant and certainly aging somewhat compared to the rest of the world. So this growing number of capitas and the growing energy use per capita will induce strong growth in demand in the next many decades. In fact, if you make a projection, global energy demand is going to go up by about 50% over the next 25 years. Most of that increased demand is going to come from developing countries. And here it is graphically. We see in the OECD countries some amount of energy growth over the next 25 years, but the big growth in energy comes from the developing countries. This shows it perhaps even a little bit more dramatically. This shows the total, absolute, not per capita, energy demand over 30 years in various sectors of the world. North America going up, that's us. Europe also going up, but look at Asia. Okay. Wow, right. A statistic associated with this is quite interesting. As these countries, China, India, cross the threshold of income where they can afford mobility, they will, of course, be purchasing automobiles. And in fact, in the next 20 years, more automobiles will be manufactured than were manufactured in all of the 20th century. Lots of people, they're getting more wealthy rapidly, and energy use will go up. Not to say that our own isn't also going up. It's interesting when you look at energy demand by sector. And so this shows the same growth in energy up to 2030, but broken up by sector. Most people, when you say energy, immediately think oil and automobiles. In fact, transport accounts only for about 25% of the world's energy use right now. About 40% of that energy goes to make electricity, to power, and about another 40% goes to make heat for both industrial processes and heating of buildings, both residential and commercial. As the world becomes richer, we will see a disproportionate growth in transport because as people cross that threshold, they like mobility. We'll also see a disproportionate growth in electrical generation because electricity is the kind of clean energy that developed countries prefer. Nevertheless, the rough proportions will remain as they are. Let me say a few words about energy efficiency and conservation. They are really different animals, although related. The energy demand, as you've seen, depends upon more than just GDP. There are many different factors: the geography, big country, small country, the climate. Heating and cooling demands here in Southern California are not as extreme as they are in the Midwest, for example. Urban planning, the structure of cities, the economic mix, factories that make things consume more energy than offices in which people just sit and think. I was a theoretical physicist, you know. So. For example, the U.S. consumes in transport energy more than 3 times that of Japan per capita. And so clearly there are differences in the way society is built and in the incentives involved in using or not using energy. Efficiency is really about using technology to pay today in the expectation of saving for tomorrow. So I might put in a more efficient furnace in my house. It might cost me more money, but the expectation is that I will pay it back in reduced fuel bills over the next many years. For people to deploy it, it must be cost effective to be attractive, or it has to be mandated by policy. And what's interesting is that efficiency may not reduce demand, because the efficiency can be misused or because supply limited situations exist. For example, if there is right now not enough electricity in China to supply all of the air conditioning needs that China might have, making air conditioners more efficient will result in more cool Chinese, but it will not reduce electrical demand. An example of misuse is what you see in the U.S. automobile fleet in the 1990s. During that time, the mileage of new cars sold went up by 4.6%. That's pretty good. But if you open it up, it tells a very different story. During that time, engine efficiency, power per unit weight, went up by a remarkable 23%, 2.3% a year. That's really very fancy engineering. On the other hand, those gains were eaten up by increases in vehicle weight and performance, 18.4% to give us the net of 4.6. At the same time, during that decade, the annual miles driven per vehicle went up by 16%, and the annual fuel consumption went up by 11%. So making something more efficient doesn't necessarily mean less use of it. You really have to conserve rather than worrying about efficiency if you're worried about energy supply. Okay, so that's enough about the prospects for demand growth over the next 3 decades or so. Let's talk about supply challenges. The first headline here is that there are significant resources. Contrary to what you might read in the ads that Walter was talking about or in other books, the world is not running out of fossil fuel resources anytime soon. However, we will see significant growth for various reasons in non-conventional or alternative sources of energy. This is a lovely chart. It shows where the U.S. got its energy over the last 150 years. And you can see back at the time of the Civil War, most of the country's energy came from wood, a little bit from coal. As the Industrial Revolution took off in the country, coal displaced the wood, or actually coal was added to the wood. And then as the Transportation Revolution took place in the early 20th century, oil consumption increased significantly. Gas has been increasing a little bit later on, and then there is a wedge associated with nuclear and renewables, or that little pink band up on top. Okay. So the lesson here, first of all, is that societies do change where they get their energy from in response to developments in technology and/or economics. And the other interesting fact on this chart is that the total amount of energy that the U.S. got from wood in 1850 is just about the same as the total amount of energy it got from wood in the last several years. Right? So the demand for energy has gone up, and we have found new sources for it in order to meet that demand. This is where the world has gotten its energy over the last 35 years and where it gets it currently. Right now, you can see that oil accounts for about 36% of the world's energy, coal 28%, natural gas 23%, nuclear and hydro 6% each. As we've looked over the last 30 years, oil has been coming down as a fraction of energy. Coal went down but is recently coming back up for reasons that we'll discuss. Gas has come up, and hydro and nuclear are essentially flat over the last several decades. The different sources of energy are used in different ways, and it is important to appreciate that as we think about how we might be able to change the ways in which we get energy. There are different uses. The world uses about 186 million barrels of oil equivalent per day. Again, forget the units, it's 186. Of that, some fraction goes to industry, some fraction goes to buildings, and 37 of the 186, again about the 25% goes to transportation. If we look first at oil, you can see that the great majority of the oil goes to transportation. A little bit and a decreasing fraction goes to heat buildings, some goes to petrochemicals, of course, and a decreasing fraction, very small, goes to power generation. Of gas, most of it goes to power generation, but significant fractions also go to heat processes in industry and buildings. Essentially, none of it goes to transportation. Coal, which we'll see is a very significant player here, most of the coal goes to power generation. Biomass, which is used significantly, as you can see, mostly to heat buildings and fireplaces, and it's a non-trivial fraction of the world's energy. Renewables, 5 of the 186 are renewables, and all of that is power generation, hydroelectric, solar, wind, etc. And then finally, nuclear provides about 3 times as much as renewables, and all of that goes to power generation. So if you put it all together, the lesson to learn from this is complicated, I know, but here's the headline, all right? The headline is that oil is about transportation, and transportation is about oil. Coal is about power, and gas is split between heating and power. Okay, those are the things to remember. If we look at where the world has been getting its energy and will get its energy over the next 30 years, these are projections of what the energy mix will look like in 2030 using reasonable estimates of what the growth rates are. You can see that right now, the world gets 85 or 80% of its energy from fossil fuels, coal, oil, and gas, with the rest as shown. Even with the strong growth rates in renewables and other sources, by 2030, under a business-as-usual scenario, most of the world's energy will still be coming from fossil fuels, coal, oil, and gas in the proportions shown. So the real question is, first of all, is there enough available to meet that demand? This is measured in energy units, showing the 3 fossil fuels, oil, gas, and coal. Right now, the world knows about 41 years' worth of oil at present consumption rates. The geologists and petroleum engineers believe that there is plausibly an equal amount yet to prove or to find. And then there are a host of unconventional sources for oil, which we will discuss in a moment. For gas, there are 67 years at current consumption rates, and about an equal amount yet to find, and vast amounts of unconventional gas that we do not yet know how to tap, in particular hydrates or clathrates in the permafrost and at the bottom of the oceans. Coal, as you can see on this graph, is the big gorilla here. Of proven coal reserves, there are 164 years at present consumption, and no one has really gone exploring for coal. There are estimates that it goes up as high as 1,000 years. Right? So there's plenty of carbon in the ground to exploit. This graph shows, it addresses the question of, are we running out of oil? It's prepared by the IEA, the International Energy Agency. And it shows how much oil is available in billions of barrels as a function of how much does it cost to produce that oil. The world in the last 150 years has produced just about 1 trillion barrels of oil at prices less than $20 a barrel. Estimates in the Middle East, the OPEC countries, are that there is another 1 trillion barrels of oil at very low prices. Outside of the Middle East, in the US, Russia, and so on, other conventional oil, about another 1 trillion barrels. And then various other sources, deep water, the Arctic, enhanced oil recovery, at prices that go up and account again for about another 2.5 trillion barrels of oil. During the next 25 years, the world will need 1 trillion barrels of oil. That corresponds to an annual consumption rate of 100 million barrels a day. The world right now uses 85 million barrels a day. It will grow to slightly more than that by 2030, but the average is 100. That's the width of this red bar. And you can see, at least if one is willing to consider all of these sources of oil at prices that are economical compared to today's $60 a barrel, the world is not running out anytime soon. I might just say a word about enhanced oil recovery, EOR. Today, on average, the world gets about 35% of the oil it knows to be in the ground up to the surface. The rest of it gets stuck. It gets stuck in the pores of the rocks due to various physical and chemical processes. There are techniques, again involving physics, chemistry, and in some cases biology, that can be used to unstick that oil, a succession of them at increasing cost. Every 1% improvement in that recovery worldwide is an awful lot of oil, equivalent to the whole North Sea oil reserve. And so consequently, there's a lot of effort that is and will be devoted to improving the recovery of oil from existing resources. Okay, that's about supply. Let me now turn to issues of security of supply. And the headlines here are the dislocation of resources geographically relative to where demand is and the consequent growing dependence upon imports of the consuming countries. Let's go that way. Good. This graph, again in billions of barrels of oil equivalent, shows how much fossil resource there is in various parts of the world. And what's shown is conventional oil, unconventional oil, tar sands and shale oil, gas, natural gas, and coal. And so let's start with the Middle East, where everybody knows the oil is. And sure enough, there's a big red bar over there. There's a lot of gas as well, but there's no coal. All right. Let's look at the US. Not very much conventional oil, but an awful lot of unconventional oil on the same scale as what's in the Middle East. Again, those are tar sands and shale oils. A good amount of gas and an awful lot of coal. If we look at Asia Pacific, China, Japan, India, not much oil, not much gas, but an awful lot of coal. If we look at the former Soviet Union, they lucked out. There's a lot of oil, a lot of gas, and a lot of coal, right? As Mr. Putin is discovering. Europe didn't do so well in the geological lottery. So what does this mean? If you take the three largest energy markets, North America, Europe, and Asia Pacific, these are the three big consuming centers. For oil, those three markets consume 78% of the daily production of oil, but they have only 10% of the conventional oil reserves. Gas, those three markets consume 61%, but have only 15% of the reserves, whereas for coal, it's much more evenly matched. So a very simple way to say it is that the coal is where the people are and the oil is where the people aren't. Right? That leads to a growing trade in energy. You can see growth over the last 20 years of exports of energy from Africa, the Middle East, the former Soviet Union, and South and Central America, and you see growing imports in North America, Europe, and Asia Pacific. With respect to oil, the U.S. now imports about 60% of the oil that it uses, and of course, consistent with this chart, it's growing by the day. Okay, so that's an issue about security of supply. Let me turn a little bit to environmental impacts, and there are really two here. One is the issue of local pollution and things that come out of tailpipes and smokestacks. To my mind, that's largely a solved technical problem. And indeed, for the 30 years that I lived in the Los Angeles basin, the air got palpably better, even though the number of vehicles and the number of people went up strongly over those 30 years. An increasingly stringent set of regulations has driven technical developments to really make things in terms of local pollution quite clean. If you go to China or India, you will see that that's not the case there. The technologies, however, exist, and it's only a question of when those countries decide to deploy them at cost. Climate change, which is the focus of this series and what I want to concentrate on, is a much more problematic issue for reasons that I want to talk about. I'm sure Jim Hansen covered several weeks ago a lot of the science, but there are two facts that for me are crucial in thinking about dealing with CO2 emissions and climate. The first is that the Earth can absorb the anthropogenic emissions only at a limited rate. We are currently dumping CO2 into the atmosphere faster than the system can absorb it. If you want to reach a better equilibrium in that process, emissions would have to drop to about half of their current value by the end of this century if we want to stabilize the atmosphere at 550 ppm, which, at least as of a few years ago, many scientists thought was a threshold above which we should not go. As you probably heard from Dr. Hansen, current thinking of some number of scientists is that the number should be lower, perhaps even as low as 450 ppm. We are currently at, just to remind you, 384 ppm. Pre-industrial was 280, roughly. This drop of emissions by a factor of 2 at least has to come in the face of a doubling of energy demand in the next 50 years. So our energy system has to get 4 times more carbon efficient than it is currently. That's one fact to bear in mind. The second is that the lifetime of carbon dioxide in the atmosphere is, for all intents and purposes, infinite on the timescales we're interested in. It's 1,000 years or so. So if we put it up there, it stays up there. And what that means is that the atmosphere will accumulate emissions during this century. And in particular, because our emissions are growing strongly, modest reduction in emissions will delay crossing any danger threshold, but will not prevent it. If you want to really stabilize emissions, stabilize concentrations, you have to turn the emissions curve over, not just reduce it a little bit. And a good rule of thumb is that a 20% reduction in emissions buys you about 15 years in crossing thresholds. We can have a look at that a little more quantitatively. These are some stabilization scenarios run by some friends at Princeton. This shows emissions of CO2 in carbon, in tons of carbon per year. This is what we have done historically. This is the projected growth under business as usual. The resulting concentration takes off with very much the same exponential if we don't do anything. If we want to stabilize at 550, let's say, we need to follow one of these green trajectories, either flat-topping emissions and rolling it off, or letting them grow for a while and then cutting back very sharply over the next several decades. If you want to stabilize at 500, it's the blue trajectories, and if you want to stabilize at 450, it is the red trajectories. Essentially, we need to begin reducing emissions right now. So that's a little bit about the science. To my mind, beyond the science and the daunting challenge of stabilizing or reducing emissions, there are all of the social barriers to doing that, and I just want to tick them off for you because they are not insignificant. First of all, the climate threat is intangible and diffuse. It can be hidden in natural variability. It's not like air pollution where you can look out your window or feel it in your chest and see it directly. It's much more diffuse. I would also contrast that with ozone, which did not become real for many people until NASA produced this picture of the ozone hole over the South Pole. And then people got serious about doing something. The second is that, unlike many aspects of pollution that we've been able to deal with, energy is at the heart of economic activity. It is so central to what we do in society that we hardly think about it because it's so pervasive. Very important is the fact that the CO2 timescales are poorly matched to the political process. As I've shown you, the buildup and lifetime of CO2 in the atmosphere are hundreds of years. The energy infrastructure, the way in which we produce and use energy, takes decades to replace. Power plants last 40 years or so, and so the power plants that will be emitting by mid-century, when we will hit 550 ppm if we don't do anything about it, are being installed and planned right now. Automobiles last 20 years, buildings last 100 years or so, and so it's very difficult, because the infrastructure is so large and durable, to make rapid changes in things. And then, of course, the political cycle is 6 years and the news cycle is a day. Right? There will be the inevitable distractions in this task. There will be a few years of cooling in the next several decades, guaranteed, because of the natural variability. There will be economic downturns that will cause people to ask, why are we spending the money to do this when in fact the economy is in the tank? And there will, of course, be unforeseen expenses, to cite current examples, Iraq, tsunamis, et cetera, et cetera. All right? All of which will act to distract society from keeping its attention on this very long-term problem. And maybe most importantly for me, emissions, the economics associated with them, and the priority that people place upon the threat vary greatly around the world. This graph shows CO2 emissions per capita against GDP per capita, so it's very much like the energy chart that I showed you, emissions in tons of carbon against GDP. It looks a lot like the energy chart. The US is up here, the EU and Japan are down here, China and Brazil, et cetera, down there. But there are two things that stick out. One is France. France is low on this chart compared to where it was on the other chart. In fact, you saw it going up through the others before. The reason is that France gets 80% of its electricity from nuclear power. Right? The second is that Brazil is lower on this chart than it was on the first graph I showed you. The reason is twofold. One is Brazil has a lot of hydropower, and the second is that Brazil powers about half of its road transport from biofuels. Okay. So there are examples of countries that have reduced their emissions successfully and still manage to achieve economic growth. Those are only two strategies. There are others, of course. However, the implication of the different levels of emissions around the globe are really stark and sobering. What it means is that in this century, emissions from the developing world, China, India, Brazil, et cetera, will be more important than those from the industrialized world. The developing world emissions are growing at 2.8% a year. You remember that big bump up in Asia in the energy consumption, versus the industrial world's emissions growing at 1.2% a year. Right now, they're roughly comparable, and they'll cross in maybe the next 10 to 20 years. And so, in fact, the picture looks like that. Emissions versus time. The developing world lower right now, but crossing over and growing more rapidly. The industrial world still growing, but growing more slowly. When you look at those numbers, there are two things that you can conclude from them. One is that when the emissions are about equal in both parts of the world, as they are now, every 10% reduction that the industrial world manages to make in its emissions, and has not yet managed to do that, that 10% reduction would be compensated by less than 4 years of growth in the developing world. And the second is, if you took China's or India's emissions per capita and made them equal to those of Japan, which is among the most emissions light of the developed countries, global emissions would go up by 40%. And remember, we need to cut them by a factor of 2. There are really two big numbers in this problem. Physicists always like to look for big numbers or small numbers. The two big numbers are the per capita use in the developed world and the number of people in the developing world. Both of those are of equal importance, and both condition the kind of solutions that you might imagine. So, when I was in academia, I would look at a situation like this and say, you got a real problem. Having now spent 3 years in business, I have learned to say this is a challenge. It is, in fact, an enormous challenge, and technology development, as we will discuss in a moment, will play a central role. And so what I want to do now is turn to energy technologies and what role they might play. Oh, I got 2 more charts, I'm sorry. This is just a reminder that while fossil fuels are the largest part of greenhouse gas emissions, they are not the only contributor to the problem. This shows greenhouse gas emissions a few years ago by source. Energy emissions comprise about 60% of the greenhouse gas emissions, but there are significant other sources as well. Land use, mostly due to deforestation, agriculture, due to nitrous oxide, and methane produced by waste are also significant greenhouse gas sources and are amenable to management as well. Right. Let me not talk about this chart. Okay, let's turn to the technologies. Here is a big list of energy technologies. Technologies associated with where we're going to get our energy, primary energy. Technologies associated with converting those energies and extracting it from the fossil resources or from the renewable resources. And then technologies that are associated with how we use that energy. Internal combustion engines, fuel cells, urban infrastructure, et cetera, et cetera. When you put a list up like this, you're a little bit bewildered at first, and you don't know what to focus on. And in fact, as you talk to people, you will discover that everybody has their favorites, right, about what you should be working on. And in the polite ecumenical spirit, you like to say that there are no silver bullets, and we need all of this. For a company like BP, who operate at scale and really want to have an impact, the right addendum to that is that, but some of the bullets have a larger caliber than others. And we've really got to focus on the things that can make a difference in dealing with these problems, all right? So how do you judge technologies? First, there's the issue of what the current technology status is and what the plausible technical headroom is. So let's look at a technology like wind, which has been around for centuries. Yes, there are incremental improvements in wind power, and I was talking with some folks this afternoon about them. No doubt it will get better steadily. But the factor of 10 improvements that we might expect in some other technologies, for example, those based on biology, where the science is still evolving and is yet to be exploited, there are clearly areas where you might expect greater progress. The second people often forget are the budgets for the 3 E's. The economics, how much does an energy technology cost relative to other options? The energy budget, how much do you get out relative to what you put in, and does that matter? And the emissions budget, how much greenhouse gas and other local pollution are you generating in the course of building and operating the technology. Another thing people forget about is materiality. The dominant thing about the energy system is its scale. It's enormous. And for a company like BP, we've set a threshold of things we can imagine producing 5% of the world's energy demand by mid-century. That corresponds to a terawatt, if you like. There are other costs. Reliability, intermittency, and so on for the renewables. The wind doesn't blow all the time, the sun doesn't shine all the time. You have to have backup systems. And then there are issues of social and political acceptability, most obviously for nuclear, but also increasingly for wind. There are a lot of big fights going on in some parts of the world about where you can and cannot put wind farms. But also, very importantly, people tend to confuse the problems that they're trying to solve. And you have to really keep your eye on the ball as to what problem you're trying to solve. There are really 2 problems that you need to solve. One is the security of supply problem. How concerned are you about the availability of oil and gas? You could read this roughly as oil price. Low oil prices, high oil prices, although it is more than that. The other axis that you need to worry about is the concern about climate change. And you can read this roughly as carbon price, not concerned at all or very concerned. And different technologies play differently to these two axes. And I want to take you through the technologies right now, and we'll see how they play. This is, of course, only notional. It's not really quantitative, but nevertheless, it gives you some way of thinking about that whole zoo of technologies. This is what goes on for the transport sector. Transport is really about liquid hydrocarbons. We're not likely to see liquid hydrocarbons, whether it is gasoline, diesel, ethanol, other more exotic fuels, disappear from transport anytime soon. The reason is that the energy density is just too good. The energy density of gasoline is about 50 times that of the best battery you can imagine right now, and about 6 or 7 times the most optimistic projections for hydrogen storage in vehicles. In fact, the energy density of gasoline is greater than that for TNT. For those of you who are technically minded, you might be interesting to know that when you put the pump nozzle in the gas tank of a car, you're wielding 15 megawatts of power. It's a rather amazing number. Right? So, for transport, where you need a lot of energy in a small space, liquid hydrocarbons are it. So how are we going to get that? One is coal to liquids. We can turn coal into liquids. We can make very good diesel fuel out of coal. There are processes for doing that. The problem is it's fairly expensive and it's awful environmentally, CO2. We can make gas into liquids by pretty much the same sort of processes. We can go after heavy oil. We can go into unexplored regions of the world. All of this is more or less conventional fossil fuel, well, unconventional, but fossil fuels, nevertheless. Biofuels are interesting. The conventional biofuels, as we'll discuss in a moment, sit about over there. Not bad for climate, pretty good for security of supply, but is the advanced biofuels that sit in the upper right and are by far the largest material option. Hydrogen for transport, we can talk about during the questions or discussion. There are, of course, also demand-side options, lightweighting of vehicles, hybridization, and to some extent dieselization that will play in this as well. A crucial notion in thinking about transport fuels beyond petroleum is the idea of the fungibility of carbon. So I'm a physicist and I like to count things simply. If you're going to have hydrocarbons, you've got to have the carbon. There are chemical processes that the chemists know how to do to decorate the carbon with hydrogens and oxygens and so on. It takes some inefficiency to do it, but if you don't have the carbon, you're nowhere. We have processes that will take various sources of carbon and through chemistry turn them into diesel fuel, alcohols, or even electrical power. But the real question is where you're going to get your carbon from. And so let me talk about that for a minute in the U.S. This shows where the U.S. gets its carbon from per year in recent years. In transport fuels, gasoline, the U.S. uses about 450 million tons a year of carbon. That's a lot of stuff. In diesel, another 200. So altogether, 650 million tons of carbon a year are used to power transport in the U.S. Let us suppose that we want to make some impact on that situation by finding some other source of carbon. Let's suppose we want to displace 15% of that. That corresponds to the height of this red line, about 100 million tons of carbon a year. So we're going to have to find 100 million tons somewhere. Where are we going to get that? Well, let's start with the other fossil fuels first. The U.S. uses about 1,000 million tons, or 1 billion tons of coal a year. Actually 1.1. There is ample capacity to take more coal out of the ground, and so we could pursue that coal to liquids technology and get more transport fuel that way. The other fossil fuels, natural gas, other petroleum, natural gas liquids, the other petroleum is petrochemicals. We need all of that already to do what we're doing with it. We're importing it already, and so it's probably not a good place to look for more carbon. So it is fashionable these days to look to agriculture as a source for fuels, biofuels. So let's look at how much carbon is in the agricultural crops. The entire U.S. corn crop was 125 million tons of carbon last year. The entire crop. About 15%, last year 20% of that crop was used to produce ethanol, which displaced 2% of the gasoline demand. You can see that if you use the whole crop, so no food for animals, no food for people, that might not be a bad idea, corn syrup, no exports, right? You turned it all, you might be able to make 15%. What's interesting is the other crops, paper, soy, wood pulp, wheat, too small to make a difference. Interestingly, in view of popular culture, is the total edible fats and oils that the country produced. So you remember biodiesel and Willie Nelson and all of that, right? The message is you can't fry enough French fries to make a difference, okay? It's just too small. The other sources of carbon that you can look to is biomass. And in a recent year, the U.S. used about 100 million tons of carbon in biomass, burning wood in paper mills, pulp, for example. The Department of Energy and U.S. Department of Agriculture estimate that with careful use of forestry resources, agricultural residues, and some planting of energy crops on currently unused land, that you could get about 650 million tons of carbon sustainably without impacting food production. So the message here is if you want transport fuels beyond petroleum, you're either going to dig it out of the ground as coal, which has got all of the CO2 issues associated with it, or you're going to grow it as biomass. And to my mind, that is the most compelling rationale for advanced biofuels. Just a word about biofuels right now. 2% of the world's transportation is powered by biofuels. It's good because it uses existing infrastructure. There's growing support for it worldwide because it addresses both security of supply, greenhouse gas issues, and also plays to the desire to sustain agriculture. Right now, it's done mostly by converting food crops into ethanol or biodiesel. In the U.S., it's the corn ethanol that is used. That's economic, actually, at $45 a barrel or more. Brazilian sugarcane is economic at $22 a barrel. The problem with both of these, and in fact with the EU's use of rapeseed and palm oil as well, is that they don't scale. These are food crops, they're not energy crops. And so, you have problems like the tortilla crisis that you probably read about in the papers, where the use of U.S. corn for ethanol is driving up the price of corn in Mexico, for example. If we're going to do biofuels right, we've got to really stop strapping it on the back of food production and learn how to fuse the food and energy chains together. So when you think about how we do petroleum, there's a whole value chain associated with exploring for petroleum, getting it out of the ground, producing it, moving it around in tankers, refining it into fuels, and then blending it. A highly developed art over the last 150 years, optimized to the fraction of a % level, and practiced well by companies like BP and others around the world. Okay, very good. I didn't expect any applause on that one. I don't know why. There is a shareholder. Good. Good. Very good. There's also the agricultural value chain, which has been developed over the last several thousand years to provide food. We grow highly engineered crops. We know how to cultivate them with great precision, process the food, and distribute it out, right? What we need to do the biofuels is to learn how to fuse these two together. And there are a host of considerations at each step on the chain. What are you going to grow? How much yield are you going to get per acre? What's the morphology of the plants? What's the chemistry of the plants? Because that will determine how we process them. Issues about stress tolerance, safety if we're using genetically modified plants, and so on. Cultivation of energy crops will be different than cultivation of food crops. We've got to optimize that. How do you move the stuff around? Because it's not food, you can afford to chop it up or liquefy it. What's the optimal way of doing that? How do we process it? We're not going to use the carbohydrates, the sugars, and starches that are used for food, but instead we need to use the cellulose, which forms the great bulk of the plant mass. That's a polymer of sugars, and we need to learn how to depolymerize that substance and then create microbes that will ferment those sugars into usable fuels. And then there's the whole issue of what fuel do you want to make. Ethanol is the current favorite. It's been around for millennia. It has uses other than fuel, as you probably all well know, but it is not a particularly good fuel. It has only 2/3 the energy density of gasoline, it picks up water, it's corrosive, et cetera, et cetera. So there's a whole chain to be optimized here, and that is largely the goal, the large part of the goal of the Energy Biosciences Institute that we recently announced that we're establishing up at UC Berkeley together with LBNL and the University of Illinois at Champaign-Urbana. It is to try to do this right. Plausible estimates of the technology and the available land suggest that the U.S. could get about 25 to 30% of its current petrol demand by 2030 from domestically produced biofuels, if it's done correctly. Okay, let me turn to power. This is the stationary energy sources. The big circle over here, you by now understand why it's big, and over on the left, it's coal. Plenty of coal in the world. It is not particularly greenhouse friendly. In fact, it's distinctly unfriendly. Gas is better by about a factor of 2, but gas is more difficult to come by. Fortunately, there are a number of big circles in the upper right. Nuclear, hydrogen power, which is a way of using fossil fuels so that you prevent the CO2 from going up into the atmosphere, but instead sequester it under the ground in oil reservoirs where you expect it will not come out for many millennia. Wind, smaller circles, solar, biomass, and so on. It's sobering and interesting to look at where the world gets its electricity from currently, or in this case, 2004. 40% from coal, 20% from gas, 6–7% from oil, 16% from nuclear, about the same from hydro, and all of the renewables are in other, 2%. Most of that is biomass, 1.3%. People burning wood and other biomass fuels in power plants. Wind is 0.5%. A few years ago it was smaller than that, so wind is going up. Geothermal, another 1/3. Solar, 0.02%, and wave and tidal, about half of that. Actually, the solar number is going up also. A couple of years ago it was 0.01%, and now it's 0.02%. Okay? Right direction. The economics are also important. This is one consistent estimate of how much it costs to generate a megawatt hour of electricity dollars by various technologies, assuming a 9% internal rate of return. You can see, the numbers will change from analysis to analysis, but the broad features are essentially right. The cheapest by far is coal at $40 a ton, and you can produce coal electricity at about 3.5 cents a kilowatt hour. Next cheapest is gas, combined cycle gas turbine. This assumes $4 gas. Current gas prices are about $7 a million BTUs. Carbon-free options, such as hydrogen power using gas, or hydrogen power using coal, nuclear, and onshore wind, are all significantly more expensive, about 30 to 40% more expensive at the wholesale level than the carbon-heavy sources. It's interesting that onshore wind competes pretty well at good sites these days with fossil fuels, which is why you're seeing wind getting deployed. Nuclear and hydrogen power, otherwise known as capture and storage, are about the same, and as I said, about a 30% increment on the cost of electricity. The other renewables, offshore wind, biomass gasification, wave and tidal, and solar at the retail cost are way up there. All right? So again, if you're worried about economics, the choices are pretty clear here. A very interesting and probably the last substantial chart I will show you is how much does it cost to save a ton of carbon dioxide emissions depending upon the price of carbon. So what you see here is the cost of electricity in the same units I showed you before for various technologies, coal, gas, capture and storage, onshore wind, nuclear, and so on, how that cost varies as you assign a cost to carbon dioxide emissions in dollars per ton. And so coal, as I told you before, starts out the cheapest if we assign no cost to emissions, but rises rapidly as the cost of CO2 goes up. Gas similarly rises. It starts higher and goes up more slowly. Nuclear is flat because nuclear has no emissions of CO2 associated with it. Similarly, onshore wind, about the same. The area where all of these start to cross is somewhere between $20 and $40 a ton of CO2. So if society is going to impose a cost of carbon and want to have an impact on carbon emissions, it needs to be at least $20 a ton of CO2. If it's below that, you're not serious. And if it's higher than that, you're probably doing more damage to the economy or inducing more dislocations than is warranted. Right? Two other interesting points on this chart are, first of all, where does solar sit? Solar is up at 250 currently. Now, no doubt that that will come down as technology gets better and as more solar is produced, but right now it's up where it is. The other interesting number is, okay, if there is a cost of carbon dioxide, let's say $40 a ton emitted, what does that do to the price of gasoline? Because after all, that's got carbon in it, and we make carbon dioxide when we use it in automobiles. The answer is that $40 a ton corresponds to 35 cents a gallon of increased cost in petrol or gasoline. If you're in the UK, it's 5p per liter. That's a relatively small number on the scale of fluctuations that we have seen in gasoline prices on either side of the Atlantic. Right? So, what this says is that by far the lowest cost way of taking carbon out of the energy system is power. And that's fortunate because that's where most of the emissions are. And if you want to take it out of transport, it's going to cost a lot more than that. The price has to be a lot higher. A word about demand-side reduction. Buildings. The world uses half of its energy in buildings. Technologies exist now, ventilation, lighting, passive solar use, to reduce that energy demand by at least 50%. The problem is changing consumer behavior, changing policy, building codes, and really business models. How does one make money out of driving efficiency into buildings? To give you an example of the kind of conundrum that exists that prevents this from happening, I lease a 120-year-old row house in London, in Kensington. It's got the typical British window system. Those of you who've been there know what I mean. No one has any incentive to improve the energy efficiency of that house. I'm leasing it, will be there for a finite period of time. The landlord does not pay the energy bills, okay? And so has no incentive either. It has to be driven in through building codes and regulation. Another big lever is the design of cities. As I mentioned, increasing urbanization around the world, the way cities are planned, where people live, how we move goods, people, how the buildings are constructed, all of that can have a great lever on energy use, particularly in Asia, where new cities are being built at a spectacular rate. Okay, I want to finish up with two sections. One is what I think is going to happen over the next 30 years, and now you're starting to see my opinions creep in. Hydrocarbons will continue to dominate transportation because of their high energy density. We're going to see a succession of conventional crudes, heavy oils, biofuels, coal and gas to liquids that will ensure continuity of supply at reasonable cost, okay, i.e. less than the $60 or $70 a barrel we've seen currently. Vehicle efficiency can be at least doubled. Hybrids, plug-in hybrids, HCCI, gasoline engines, diesel, are all technologies that can be used now. They exist. Well, not quite the plug-ins, but they will soon, to reduce or to improve vehicle efficiency. It's not so much a question of developing these technologies as having the economic and political muscle to force their deployment. Local pollution is controllable at cost from vehicles, catalytic converters and such, better fuels. CO2 emissions, as I mentioned, are only about 20% from road transport at the moment. Hydrogen in vehicles is a long way off, if it's there at all, and we can have a discussion about that if people are interested later on. In the power sector, coal for reasons of security and gas for reasons of cleanliness will continue to dominate heat and power. Capture and storage, hydrogen power will be practiced if the world is going to address CO2. Nuclear energy for reasons of security and CO2 will be a fixed, if not growing, fraction of the power mix. In fact, I would go so far as to say that if the world is going to get serious about CO2, there are two supply-side technologies that are absolutely essential. One is capture and storage, and the other is nuclear. And they will be deployed in varying mixes around the world, but those are the only two that have the potential to scale to the required magnitude and to be economic at the same time, at least right now. Renewables will find some application. Wind will probably go to about 10 to 20% of power, but they'll remain a relatively small fraction of the total energy mix, and we will see advanced solar perhaps as a wild card if the right developments are made in materials. You could see solar really take off, PV. Demand reduction. I'm somewhat of a cynic about demand reduction. I think it happens only when people are forced to do it either because of economics or because of policy. And both of those, or either of those, is a pretty difficult act for a government to pull off and still stay in power currently. Finally, at least according to the picture I've tried to paint for you, which has been, I think, largely factual, CO2 emissions and concentrations are going to keep going up unless the world really gets its act together, and that's going to be a very difficult thing to do, I believe, although we're starting to see some progress toward it. Last word, necessary steps around the technology. It is not just about the technology. We need, I think, a technically informed, coherent, and stable set of government policies about energy. We don't have that right now. I think we know what to do. The problem is getting the system to do it. And what we need to do that, I think the key is to have an educated public. Because the public, if they're educated, presumably we can educate the decision makers as well, that will give the decision makers license to make the difficult decisions that need to be made. In terms of technologies, for the short and medium term, government should avoid picking winners and losers. It should not be preferentially favoring one technology over the other. Emissions trading is one very good way of doing that. It really puts the focus on how do you reduce carbon at the lowest cost. And one wants a level playing field for all technologies. You should not favor one over the other. For longer term, there are lots of areas where we can be doing pre-competitive research. The gas hydrates I mentioned, fusion, advanced fission, advanced PV, advanced biofuels, all are areas that are ripe for research. From the business side, businesses need a reasonable expectation of the price of carbon. If an energy company is going to invest a significant amount of money in a low or zero carbon project, which might cost $1 billion and is expected to pay off over 20 or 30 years, it has to have some reasonable expectation that the reductions in carbon will still matter 10 or 20 years from now after 5 or 10 congressional cycles. All right? Markets are one way of doing that if we can keep them in existence over many decades. But, you know, the world doesn't have much experience in carbon markets yet in understanding the fluctuations and evolution of the price of carbon. So this is a problem. And finally, I think universities, national laboratories must recognize and act on the importance of energy research. Gratifyingly, we're starting to see that in the last couple of years. And a particular area that I think is important is to educate not just technologists and not just policy types, but people who can speak both of those languages, because the technologies that will get developed will depend upon the policies that are in place. With that, thank you for your attention, and we'll have some time for comments and discussion.
To again thank all the people that have contributed to making this event possible. I also want to especially thank drivinggreen.org. They have actually volunteered the credits to offset all of our contributions, our carbon contributions, coming to the event tonight. So I want to thank them especially for that. Okay, I'd like to now introduce our other panelists. I think you all know Steve quite well by now. We asked our distinguished dean, Ernst von Weizsäcker, the dean of our Bren School of Environmental Science and Management, to join our panel. And I was very gratified that Ernst agreed to join our panel for a couple of reasons. First of all, he has real-world experience on this problem. He was a member of the German Bundestag, which is roughly equivalent to well, not really equivalent to our Congress, but somewhat like that. And I believe he actually wrote some of the legislation for the use of renewable energy in Germany and has strongly influenced that process. In addition, Ernst has written a fascinating book called Factor 4, which he gave me a copy of, and I tried to read while the kids were screaming last night, parts of it. And it's really it's a magnificent work about the role that improvements in efficiency can play. And so I'd like to start the panel discussion by giving Ernst some time to talk a little bit about the potential role he sees efficiency or other things playing in this problem, and any other comments you'd like to offer.
Okay, thank you, David. It's a great pleasure. I very much liked that talk.
Thank you.
As a scientist and as someone having been exposed to politics. I mean, what you said about the consistent policy of making carbon or energy more expensive and not losing power, that was quite right.
Yeah.
But this does not mean that we cannot act. And one precondition for rational and strategic action is to know about the potential for doing better than we presently do. And here I have a little bit of a difference of opinion. That book, which David kindly mentioned, Factor 4, with the subtitle Doubling Wealth, Halving Resource Use, essentially says in buildings, in vehicles, in appliances, in agriculture, in chemicals use, etc., wherever we care to look, we can do 4 times better, not just 2 times better. You said in those last slides, buildings can be constructed so that 50% of the energy is saved. My wife and I are in the process of having a house built which, according to the architect, will save 90%. And then has some solar power on the roof, and that will more or less take care of the rest. So this is doable. And my friend Amory Lovins, who is actually the co-author of that Factor 4 book, says you can do cars that do 150 miles a gallon.
Right.
And this is perhaps a bit eccentric if you look at the costs. And I then come back to you saying the cost question is indeed essential.
Yeah.
Now, let me, in this context, just repeat something that I said 10 years ago when I was Member of Parliament. Well, we could politically agree on a long-term strategy of increasing energy prices more or less in parallel with the efficiency gained during the previous year. So if the statistical office establishes that, for instance, the mobility efficiency has increased 2% in 2006 then politically it's decided, it's an automatic decision that the mobility energy prices go up by 2%. Then by definition, there is no additional suffering. And still, there is a long-term signal for investors to compete for efficiency and to invest in that.
Right.
And I believe if we were politically able to engineer this kind of track, we would arrive at that factor of 4 by, let's say, 2050. Now, I stop here because I'm so curious about your reaction.
You have a great deal of experience in the political world, which I don't, and so I will not say that that sounds so simple it must be the physicist's solution, because you, in fact, have lived in the real world. On the other hand, what I look at is prices of gasoline go up in this country, and people get very upset. It takes them a long time to switch to more efficient vehicles. We can't tear down the houses that we have right now. We can do that with new build, as you said. And the other problem is to somehow get around the developed world perspective, for which some of these things may well work, and think about the people in the developing world, where in fact, the question is, can I just materially improve my standard of living? I'm climbing up that curve, and I will do it in the most cost-effective way possible.
Sure, but for developing countries, increasing efficiency is actually more profitable than it is for us.
Yeah, right, okay, but you saw every country more or less on that same universal trajectory.
That is right. I mean, this is history.
Yeah.
And of course, as a scientist,
Yeah.
I'm glad that you are so much relying on empirical data.
Yeah.
I appreciate it.
Yeah.
However,
Good. Good. It's always
the future
yeah.
is not visible in empirical data. This is projections based on assumptions.
Right.
And politics is meant to change the assumptions.
Right. So I'll tell you one story about prediction. A few years ago, if you look carefully at the China graph, which we look at a lot because it's a big player, it was actually not tracking with the universal curve. And there was discussion among the Chinese government, we're going to double energy use and quadruple GDP, because if you just followed it along. And sure enough, though, in the last 3 or 4 years, with perhaps better data, China has fallen right into that same universal curve. So I don't know if it's a theorem, but it certainly looks like most countries, as they develop, go through that.
The Chinese had so far 10 completed cycles of so-called 5-year plans.
Right.
And 2 years ago, they adopted the 11th 5-year plan, which is the first one strategically saying we are going to improve energy efficiency.
Right.
And if you sort of extrapolate
Yep.
what they now commit themselves to do to something like 30 years, it will be a factor of 4. Now, I'm not saying that they are going to reach it.
Right. Yes. But that's what matters in the end.
At least now there is, for the first time, in the 11th, not in any of the earlier 5-year plans, a political commitment to do it. And they know they won't reach it without some work on the prices.
And so this is a challenge for them also as they try to navigate the internal tensions in China as well, with rapid urbanization and people moving out of the countryside and aspiring to higher standards of living.
I mean, since you brought up the topic of China, what do you think is the scope for cooperation between China and the U.S. in terms of moving forward in this problem? I mean, there's this oft-quoted figure that China is building, approximately 1 new coal-fired power plant per week. And I think it's actually, we figured out it was a little bit more than that.
Yeah.
And it seems that if we're going to make progress at all on stabilizing emissions, we're going to have to, well, that's going to have to change.
We've got to develop the sequestration technology, prove it. Again, it's plausible, but we've got to really prove it. And we've got to drive the cost down enough to where it's within the noise of unsequestered coal. And I think there's ample room for many demonstration projects that look at different variations of technology, of geological setting for sequestration. Great opportunity, China, you do one over here with this technology, we'll do one over here with a different technology, mix the teams up together and really co-develop these things. A lot of scope for doing that.
If you're talking about China and America, first, it's indeed the two most important countries, and both of them are not in any meaningful manner part of the Kyoto Protocol, and that is the tragedy.
Right.
We at the Brent School, with Oren Young's help and others, are trying actually to develop this Sino-American cooperation on climate change. Now, one of the things that China may be able and willing to learn from America is what just happened last week in Texas with Colbert Kravis Roberts willing to take over TXU and environmental defense coming into the deal and saying, well, instead of 11 new coal-fired plants, maybe 3 will be enough. And if that could be, that philosophy could come into China, that would be actually economically beneficial for China.
But just for our audience, is it correct that the plants that China is building today, the coal-fired power plants, cannot easily be retrofitted for carbon capture?
That's correct.
So, do we have the ability right now to actually share that technology?
No, no one has built really a full-scale sequestered coal-fired plant yet. We have on the drawing board a project to do that in Carson, California, 100 miles down the coast here, that will use petcoke, solid waste from a refinery, to make about 600 megawatts of power and separate out the CO2. But it's a technology that remains to be proven. It's very plausible, but no one's actually done it, and then it needs to be optimized.
Well, the combined cycle coal-gas plant is meant to more or less automatically separate carbon dioxide.
Right.
And then the syngas is essentially the energy carrier.
Well, you want to get the CO out of the syngas, so you really
that is right. The CO is that's a different. But then at least the separation part is done.
That's right.
The storage part not.
Right.
But
so you could build them capture ready, if
Yes.
you like. That would be about a 20% increment on the cost when the technology is fully developed.
Yeah.